if you let this one go away, something left, are they constants? Is K constant?
Yes.
Is Q constant?
Yes.
Is R constant? Yes. If you want to detect the field at this location, R is constant, right? Therefore, this multiplied this divided by this square become a constant for this special location. If you change the R is larger, therefore denominator is larger. These two doesn't change. Therefore, the value becomes much smaller, right? Which means the field close to the source stronger. Away from it, it's weaker. Oh, that makes sense to us, right? Okay. That's it. We got it already. If you remove the small q, we got a constant for particular position. Therefore, this small q, it has a very beautiful name. It's called test charge. We just make use of it, but finally we remove that one. Okay? All right, so the definition of the electric field becomes F divided by Q. That's it. What's this Q? This Q is the test charge here. Therefore, we basically have an electric field meter. The meter is based on this definition. Okay? And of course, the field is a vector, and the force is a vector. Why the field is a vector? It's very simple reasoning. Oh, this is a scalar, but the force is a vector, right? Vector divided by a number, that's still a vector. Otherwise, this is the equation, it will not be equal, right? If two things are equal, they have to be the same thing. So this side is a vector, therefore this side must be a vector. All right, here comes another thing. This ratio basically tells you the magnitude of the field, right? How strong it is. What's the direction of the field?
We do not know.
Well, we don't know, but you know it indirectly here.
Yes, opposite if they are opposite charges.
If the force is positive, means it's repulsive, right?
Mm-hmm.
If force is negative, it's attractive. Therefore, you have positive sign, you have negative sign, which means two directions. One is that way, one is backward, right?
Yeah.
Okay. Therefore, this is the equation. If F is a repulsive, this one must also be repulsive, right? If F is attractive, this one must also be attractive. But
yeah.
Which one is positive? Which one is negative? It's not clear. You can assign this direction positive. You can also assign this direction positive.
Yes, it's arbitrary.
Therefore, you have to be the boss. Otherwise, the whole world will be in a mess. Oh, you want this direction positive, or you want this direction. No, we don't do that. So everybody should make an agreement here. Therefore, everything is in a good order, right? Therefore, for the direction of this field, we have to have an agreement. It's called direction convention. T-I-O-N-S-I-O-N?
This one.
Okay. We define the direction of the field this way. This is very important, okay? I label it double star, which is even more than the magnitude of the field, okay? The direction of the field is defined as the force direction of the test charge, or change off to on. I think on is better. The force direction on the test charge. And what kind of test charge? You can use positive charge as test charge. You can also use negative charge as test charge, right? You have two options. So which one you mean here? Because different kind of charge, the force direction is reversed, right? Okay, you have to make it very clear right here. Positive charge.
Always.
Always. The test charge must always be positive. You never use negative charge as your test charge. Otherwise, it's in a mess. All right. Not too bad. That's the first point. The second one is how to describe the electric field. It's not easy. It's invisible. It's colorless, smellless, and nobody ever seen it before. So how can you describe the electric field? But human beings are so smart. They got it already. Okay? And I checked my storage room in the lab. We don't have that device yet. I plan to buy one for you. And I don't know when it's going to come. There is a small device which is a transparent plastic container. Inside the container, we put in a lot of oil, special oil. And inside the oil, we put in a lot of tiny metal pieces. And on the container, at the middle, at the axis, there is a hole crossover. Okay? We can put in a magnet inside. When you push a magnet inside the axis, all the tiny metal pieces inside the oil will be aligned by the magnet, right? Therefore, the magnetic field will be visible, right? Yeah, we can do the similar things for electric field in the lab. Okay, in the future, but I don't know when. All right. But even if we don't have those devices, based on this discussion here, we can still do it. And for example, you have a positive charge here. What's the shape of the electric field generated by this charge? It must have a spherical symmetry, right?
Yes.
Different shell, you have different strength. The far from this charge, the weaker the field is, right? But you can visualize this in your mind, but in a picture, how? For example, this point, what's the direction of the field? The source is positive, right? What's the direction of the field at this location? Yeah, that's why I give you a double star here. How do you know the direction of this field? Right here. What do? You need a test charge, right? What kind of test charge? A positive charge, okay. If you assume there is a positive charge here, how they react each other? Repel, therefore, you will have a force goes this direction, right?
Yes.
Therefore, this direction is defined as the direction of the field.
Okay.
Therefore, right here, the field goes away from this point, right? How about this point? What's the direction of the field?
That's down.
Yeah, it's repulsive because you have to put a positive test charge here. Therefore, it goes down this way. And how about here?
It's left.
See, it it goes this direction, but if you make it longer, it must go through this charge, right? And how about here? That way, okay. How about here? Here, how about this position? You see? How about this position? How about this position? Oh, see? You got the shape? It's very easy. How about this? You don't see this point. How about this point? You put a positive charge there, repel each other the same direction here, which means on this line, every position is outward, right?
Yes.
You see, they have a spherical symmetry here. For positive charge, the electric field is going outward, spread out in the whole universe.
Each direction.
Yes, every direction, basically. This is the 3D, but I can only do 2D here, right? That's the shape of a single positive charge. That's the shape of the electric field. And another thing is where the field is stronger.
Closer.
Yes, why closer?
Because of the equation.
Oh, because of the equation. Yeah, that's a good answer. And can you show graphically?
Because the r squared.
Yeah, r squared. Yes, of course, theoretically. But can you use those lines to tell people where the field is stronger? Of course, close to the charge is stronger. But what's the property of the lines closer to the source? If you draw a small circle here, draw the same side of the circle here, how many lines inside this circle?
2 there.
See, one here, 1, 2, 3, 4, right? How many here? Just 1. That's called what? Density of lines. Which means in a unit area, how many lines you have. If you have more lines, which means right here, the field is stronger. If you have less line, which means the field here is not very strong. Okay? Those lines has a special name. We call them electric field lines. We use those kind of lines to describe the shape of the electric field. Okay, if you can do this one for a single negative charge, what's the shape of the field?
Opposite.
Okay, what's the direction of the field right here, for example? How do you make a decision?
Toward. It has to be a positive charge. It's toward.
Oh, you have to put down a positive test charge here, asking what's the force direction on it, right? They will be attracting each other, therefore going inward. And how about here? Going inward. How about here? Going inward. You see? You can do this yourself. Oh, that's the shape of the negative charge. All the electric field lines, they are going inward. And of course, still, the density is much higher, closer to this charge, and much smaller, away from it. See? Those lines are very good to show you the shape of the field, but they have a few properties. I don't want to spend time to write them down the board. A few of them. First one, those lines are imaginary, not real. People created them, just try to have a kind of a convenience to describe the field, okay? Those lines are imaginary. Secondly, those lines, see, always going out from positive charge, right? Always going out from positive charge. And this picture, those lines always going in to the negative charge.